Okay guys, today we're gonna do photoelectric effect. Photoelectric effect, what is this? Okay, let me just write down it first. Photoelectric effect. Right. Photo, this implies light. Electric implies electricity. So what does this mean? Photoelectric effect. It's something to do with light and something to do with electricity. What does that mean? It means we'll find out later. Anyway, so in 1887, a German scientist called Heinrich Hertz, this guy did an experiment where he emitted a UV onto a metal, and he observed that electrons came out. Likewise, we define photoelectric effect as a phenomenon where when you emit radiation onto surface of metal, you get a electron coming out. That's the definition of the photoelectric effect. So photoelectric effect is when you radiate radiation onto a metal surface and you get an electron coming out. Very simple. And also you call the electron that this electron coming out due to this as photoelectron. The reason why we call it photoelectron is because it's an electron that's gotta do with photo, so that's gotta do with light. Alright? Light did this. This electron came out because of light. What actually happens in this phenomenon is that when you have an atom of a metal, there is this electron of an atom, and when you get radiation onto it, this thing gets excited. This thing gains energy, so it goes up. When it has more energy, it changes its energy level. It goes higher. And when it reaches the infinity level of energy, then if I just put a bit more energy on it, then this electron just gets off. And that's how electron comes out of the metal when you shoot a photon. And by the way, the light is called photon. That just means that what do you call it? Photon is just a wave packet. It's a discrete energy thing. So, yeah. Next slide. When you have this atom and I already explained that. Why am I doing that again? How do I do this? Okay, bye. So we did an experiment using this weird result. Then that experiment was basically making a circuit with a plate looking like this, and that's just a connection, and you have this positive terminal on a negative terminal, positive terminal on this side, and you put that into a vacuum container. so that nothing else can distract our observation. We're trying to control all the variables. You know from last year or last year about the controlled variable, right? So we have this kind of container, and basically what happens is, what you do is you given some light, a radiation, and when it hits the metal plate, it will emit photoelectron, which will be attracted to the positive terminal here, because you know that this terminal must be positive and that terminal must be negative. And since this thing is basically an electron pump, electron just flows and flows and flows and reaches here. That's negative. It has more potential, so it's just making that potential gradient. As soon as the circuit is made, the current is going to try to flow this way, like that. Okay. So, and we know that radiation excites the electron of the metal, and and when it gets the radiation, the photoelectron is emitted, and this is attracted by positiveness here, and the circuit is made because now we have a flow of electron. That's the current. And we can measure how the relative size of the relative numbers of the electrons emitted by having this ammeter, because the higher the reading is, that means more electrons have been emitted, right? So that's basically an experiment, and the observations were kind of striking to the classical physicists. That's because regardless of the intensity of the light, photoelectron came out anyway. If you had a really weak light, and you cast it onto the metal plate, you still get the... Okay, let me phrase it again. So, when you cast the light, right. So the scientists realized that if the frequency of the light is not above a certain level, no photoelectrons come out, regardless of the intensity of the light. So, however strong the light was, there was no electron coming out when it was below a certain frequency. We decided to call that frequency as a threshold frequency. That's a good name because this tells you what it means. Not like other names, which we don't know what that even means. So, we found out that for light to create a photoelectron that frequency, the light had to have a frequency that's louder than that. That's what happened. So, yeah, that's the first thing they observed, and the second thing they observed was that even when you had a light that was really weak, but if that that light had a frequency greater than the threshold frequency, then the electrons came out. That's good. That's really good, right? That makes sense because it shows that it suggests that the energy. Okay, we'll get to that later. And the third thing was that when you the photoelectric current depended on the intensity of the light, and that's because greater the light, but that's because intensity of the light is proportional to the number of photoelectrons. And if you have a greater electron, okay, blah, 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 blah. And the fourth thing is that when you have this is the last thing, this frequency, if the higher the frequency, if all the frequency I'm talking about was greater than the threshold frequency, then the maximum kinetic energy of the electron depended on the frequency. That's it. These four are the observation that marks the start of these mark the start of the quantum mechanics. Right.